Okay, again, so I am Brock Palin. I'm one of the admins at Kane High Performance Computing. We operate the systems Nix and Flux, but we also are your contacts for things like the Exceed resources and things like that. And also what we'll show here will actually apply to a lot of the different systems that happen to use PBS. There's going to be a couple of things that's going to be Flux-centric, but a lot of the stuff we show here will actually translate to other batch systems or other systems that use PBS. You should be able to see my terminals now. I'm going to be doing these examples on Flux Login. So real quick, what is PBS? PBS is our batch system, so this is how you actually interact with the cluster. It's how you queue up a large quantity of work that has the cluster do on your behalf. So if you have 50 CPUs or 100 CPUs, it's what figures out, okay, all 100 are in use, so this will wait. It'll automatically start the next one, an next job when resources free up, and it's basically how we make sure that our 10,000 processors on Flux actually get allocated out in an even way. Machines that have issues don't get new jobs on them, things like that. So everything goes through what's called PBS. So PBS we're going to focus mostly on what's called a batch job. That is basically you batch up. You take a set of work and you make it kind of run standalone. So you take it, you put it together in what we call a batch job, you submit it, and the cluster runs it for you, and you get to go home, sleep, and it emails you when it's done. That's as opposed to interactive, which is like me sitting at my laptop here and typing commands and watching output come kind of in real time. That's like interactive. We will show later how to do what's called an interactive job, which is great for debugging and things like that. For the most part, most people need to do large quantities of batch jobs. So probably the most important things we're going to dive right into is creating something called a PBS script. A PBS script is basically a text file that has the two pieces of information. It has directives to PBS itself, which will have things like charge against this account, email me, I want this much memory, I want 15 cores, that sort of information. And then another hunk of information, which is how to actually run your code. This would be like your executable, cd to this directory, run this executable, zip it up when I'm done, and back away. So these are just plain text files. You can create them on your own machine. I generally create them right on a cluster using one of the text editors here. So I'm going to so I'm going to create a file called pbs.txt, and anything that starts with #PBS is special. So these are the directives to the batch system. So there's a couple of common ones. Capital N is a job name. It doesn't have to be unique. It's not even required. It's optional. If you don't have it, it just gives it some default name. It can't have spaces and a few other things, but if you try to submit a job with an invalid name, the system will just reject it right away. So something like job name with numbers in it and stuff is fine. Then the next thing we want to do is we want to be notified. So uppercase M is an email address I want to be notified at. My email is brockp@umich.edu, so I'm going to use that. Lowercase m is when to be notified. So there's a couple different values here. I can put N for never. I can put B for beginning, so when a job starts, it emails me, because it may be queued, right? It may be waiting to run behind LabMate or your other jobs. There's E for email me when it ends, and then there's A for email me when it aborts. And so I can combine these together. So I can have ABE, which means email me when it aborts, or it begins, or when it ends. So that's a common collection there. When you really get going, a lot of times you want to change it to this, and then if you have a lot of jobs, maybe you want to change it to that. So if you have a lot of jobs, you're just going to kind of watch it manually to see when a large chunk of jobs is done. So you don't want to get an email for every job that ends, but you want to know if it fails, so you leave abort. But we're going to go ahead and say email me when it starts and when it begins and when it ends. The next piece of information I want to have is something minus capital V. It's just something our system requires. If you don't have it, you're going to have problems. So just always include #PBS minus capital V. What it does is it copies the submit environment to the batch environment. So this allows you to change environment variables. If you don't have this, you'll get errors. So just always include that. So what comes after this is the resource information. This is how many processors and stuff I want like that, and those always go on minus L lines, lowercase l, and lowercase l can appear multiple times. So I want things like wall time. In this case, it's in the format of hours, minutes, seconds. So I can say something like 3600 seconds, so this is 1 hour, or I can say give me 1 hour. This is wall time, not CPU time. So if I ask for 12 processors, I'm going to get 12 processors for an hour, so a total of 12 CPU hours. If a job ends early, that is the last line of the script finishes before the time's up, fine, you're not going to waste any resources. It'll end and you'll get an email, and that email normally says how long it ran for. But if you request too short of time, we kill it. So when you hit an hour and you're still running, we kill off your job. So you always want to request more time than you think. To check how much time you can request, the maximum amount of time you can request on like the Flux queue is 672 hours. So that's like what, 2 full weeks, 14 days. And you can always figure that out by typing queue_stat minus q, which is query the queues. So some of the other L's, notice I can have more than one of them, is I can say proc. So in this case, I want to have, let's say, 6 processors. And I'm going to separate with a comma. Pmem equals 1 gigabyte. So Pmem is the amount of memory per processor I want to request. There is a default quantity. The default quantity is 768 megabytes. So what this would be is my total memory would be 768 megs times 6 processors is 768 times 6, about 4 gigs of memory. So Pmem is memory per processor. So it's, and you want to use Pmem rather than mem most of the time, because mem is squishy about where the memory is supposed to be, and with Pmem, you know you're going to have 768 next to each processor you can actually touch. Saying proc equals 6 does not put all your processors in one node. So if you're using a shared memory code like pthreads or OpenMP where everything needs to stay inside one computer, you need to use a different syntax, and I'll touch on that at the end in the more advanced topics. But proc equals 6 is the one that's going to start your job the fastest, because that'll say give me 6 processors in any number of machines. So I may have 6 machines with 1 processor each, 1 machine with 6, 2 with 3, 1 with 3, 3 with 1. You know, they'll be spread all around, so we have more options to start your jobs. The more restrictive you get on your resources, that is longer runtime, more memory per processor, specific geometries, you know, like 12 processors per node or something like that, the harder it is for us to start your jobs, because we'll have less options to possibly start your code. On Flux, this generally isn't that much of an issue, but for people who are trying to request specific machines, sometimes it can take a little bit longer. You can request other things. You can request something called a GRES, which is like a software license for things that are licensed. We need to track those ahead of time. You can't just arbitrarily put stuff in there. But this is the kind of thing you can request. So in this case, I want 6 processors, 768 megabytes of memory per processor, and for 1 hour. The next chunk is the credentials I want to submit to. So on Flux, it's minus Q Flux. There is Flux M for large memory flux, and Flux G for GPUs and things like that. And then I need the account to charge from. That's minus capital A. So I'm going to use CAC staff Flux. This is your allocation or account. This is the thing that actually lets you run jobs. If you don't have one of these, you really can't run jobs. I'll show you later how you can find out what allocations you have available and what resources are available in them, and how to check on the status of individual allocations. It takes us a very short period of time to make allocations, so if you need an allocation to use resources, just let us know, and we can set you up with the needed information how to get this started. Lastly, there's one last little thing you have to do. It's an L, so it's a resource line technically, but you need to have QoS equals Flux. So again, useful information, when to be emailed, where to be emailed at, job name, minus V, again, is just required. Resources, so wall time, processors, memory, and possibly software licenses and other things. And then where does it run against? So Flux, your allocation to charge against, and your quality of service. Okay, so this is the PBS part. This is the stuff that you that you talk to PBS with. What comes afterwards are just normal commands. So I could put stuff in here like print which directory I'm in, you know, just like I can type over here. So pwd prints that. Well, here's what it's going to do. Anything that starts with a pound is a comment, so you can comment stuff. And you notice I'm using liberal white space. I can use all the white space I want. So pound without capital PBS after it is just a comment. Pound with capital PBS is special. So let's cd to the directory. These are some more advanced topics. Let's print out all the processors we were assigned. And so that's basically all I'm going to do. But normally I would have like run an executable in here, something that runs for a long period of time. That'd be MPI run, or my regular executable, MATLAB, something like that. But all I'm going to do is use normal Unix commands, you know, cd, cat, print working directory. So I'm going to save this. So this is my PBS file. And then I'm going to submit it. So before I submit it, are there any questions about what I have in that file right now? Ken asks, you need to start with the shebang bin sh. No, you actually don't when you're submitting it. But if you want this to be a script that can run standalone outside of PBS, yeah, you're going to need to add something like that. But actually you don't with a PBS script. It's actually implied. And if you want to change what shell, so by default this is evaluated by bash. If you want to change what shell you want this evaluated as, you can use pound PBS minus capital S and say like bin CSH, and then you can use, you know, C shell logic in here and stuff. This is really just a shell script. Everything that comes after here is just a shell script. So you can put if statements and loops and other things in there. So you can change your shell, but by default it just gets evaluated as bash. Other questions? Okay, it looks like we're good. Okay, so I have this PBS file. How do I actually submit it to the system? Well, I can submit it with the command qsub. And so give it the text file, and there it goes. So it gives me back this number. This is what's called my job ID. This is what you need to keep track of. When you writing a question saying, hey, I had a problem, we pretty much always going to want the job ID and the script that you use to submit it with. You can resubmit the same script multiple times. So now that I've submitted this job, I could edit the script for, say, a new input file or some other change and resubmit it, and the first job is going to be unaffected. We do copy the PBS script when you submit it. Your code, input, stuff like that, we know nothing about, so we don't copy those. So those, of course, need to stay put through the entire duration of the job. So how can I check on the status of my jobs? If I use the command qstat, if I run qstat by itself, I get every job, which is a big honking list. So that's not necessarily what I want. So if I use qstat minus u, a username, it shows me just my jobs. And so here's my job. Here's my job ID, which I can use to get extra information. There's the queue I submitted to. Remember, we set that pound PBS minus q flux. Job name. It says I'm asking for 1 hour. And my state is currently queue or queued. So I'm waiting to run. So this is a job waiting to run. We only start jobs every so often. And so I can have a lot of these things queued up. I can have hundreds of these queued at a time, just waiting to go. If you do need to do hundreds, there might be easier, more advanced topics like job arrays or automated submission instead of actually editing 100 PBS files. So this job should start soon, unless I made an error. And so what I can do to check on a job is I can take this job ID, and there's a command called check job. And minus V is pretty much always the most useful thing. Run it on that. And so this gives me all the needed information. Oh, it looks like my job started because see, it's in state running. If you run check job on a job ID and it says it doesn't know about it, that just means the scheduler hasn't gotten around to reading from the system any new jobs that have been submitted. So just wait, because again, we only start jobs every so often. But here's all my credentials, you know, user, Brock P, my group, my account I submitted against, or my allocation I submitted to Flux and my QoS. As for, I've ran for 0 of 1 hour, and I was queued for 1 minute. I asked for 6 tasks or 6 processors, and the tasks are defined as a processor with 768 megs of memory. So that's what we do when you have that outline and you say prox equals 6 and pmem equals 768. We define this thing called a task, which is a processor plus memory together. And so here's the machines I was actually assigned. So I was given 1 processor on 6 different machines, rather than 1 machine with 6 processors. So that prox equals 6. See, my processors got spread around. And I've got some other information in here. But if the job had not started because I typoed this account name, or I don't actually have access to that account yet because my advisor hasn't said to add me, you'd see messages down here saying that it violates that, does not have permission to access that account. If you're ever curious, because the information down here is generally not that useful, you can send us an email with the job ID and the message you see, and we will try to interpret it for you. Okay, so qstat minus u, my username, shows my job, and see it's now in the C state, or completed. That does not mean canceled. It could mean canceled, but it also means that it ran successfully. So the states are Q for queued, R for running, C for completed, and H for held. Held can be automatic or manual. So the most common ones you're going to see are queued and R. So qsub, submitted job, qstat, check on the status of job. A qdel, so if I submitted a new job and I wanted to delete it, I would take this job ID and I'd run qdel, that job, and it's now gone. So let's run qstat. See, I have a second completed job, but see, this job never actually ran. It's because I deleted it before it ran. Check job minus v gives you extra information on job. So qstat only lets you see based on a user or everything. So there's a more useful command called showq. So if I do showq minus r, it shows the running jobs. But what I really want to do here is I want to do showq minus r minus w account equals CAC staff flux. So the account again is like your allocation. So when you run on Flux, this is, you need one of these to run against. So this lets me see CAC staff. There's nothing running in it now because my job's all finished and nobody else is using it. So this lets me see how many processors are in use. So if I look at like a different allocation, like Crash Project, I'll see that they have 2 jobs running, one using 200 processors and one using 64. And so they have 264 processors in use. So that's how you can look at an individual account. You can look at, the W means where, so there's user. I can look at just an individual user's jobs. I can also look at only idle jobs rather than running jobs. Or I can just get rid of the running or idle thing altogether and see everything. So that's showq, which can be way more useful than a qstat, but qstat generally responds faster than showq does. Sometimes showq will take a while to give you an answer. So again, qsub, submitted job, qstat, look at status of jobs. Showq, also look at status of jobs, but lets you sort by things like account, user, group. Qdel, deleted job, check on the status of a job. So I ran that first job, and I look in the directory now that it's done. See this? These 2 files here, job name, .o and .e. We're going to want these normally too, because if jobs don't run right, these are the log files that gets created. And so what they are is the text that would normally be printed out. If I ran this script interactively, it would print out some messages. But I ran in batch, so what do? We capture it in these files. And so if I look in this .o file, you'll see a directory name, and you'll see a list of host names. Well, why is that? Well, if I look at my PBS script, I had in here the command pwd, which prints out the directory I'm in. Because that wasn't redirected to a file, it ended up in this .o file, and there's the result. Cat PBS node file is special in the sense that $PBS node file is an environment variable that points to a file that has the list of all the processors you were assigned. And so by typing cat that, if you remember from my intro Linux commands, cat just throws out the contents of a file. These were the 12 processors, the 6 processors I were assigned. So this is handy for debugging if you always end up on the same machine and stuff like that. So any text that would normally show up if you ran this by hand, it gets captured in these .o files. Any error messages go into .e file. I have one thing. I print out my loaded modules to error in my environment, so I get that in there. But you may get other error messages. So when a job doesn't run right, be sure to look into .o and .e files. These do not show up until the job is done. So if you want to look at them earlier, use a command called qpeek, which there's help for if you run qpeek --help. But if you do qpeek space job ID, it'll show you the .o file thus far. qpeek -e job ID, it shows you the .e file thus far. And if the file is really long, you can use the minus number or -f or -t or -h to only look at the first few or the last few lines of a file, rather than looking at the whole thing. Okay, so that's PBS. That's the very, very basics of it. I threw into the chat box earlier a link to our PBS documentation, which has all of this again, along with some more in-depth examples. It also includes some more detailed information. And I'm going to go into some stuff too. But some things you can do with PBS, you can do dependencies. That is, you can make dependencies between jobs. So you can submit a job and say only run after this job or this group of jobs have finished or failed, or I don't care, just run it afterwards, things like that. There's also something called a job array that lets you submit a single PBS script but have it run n times, and you get an environment variable, PBS array ID, that just goes 1 through n, that lets you kind of run multiple copies of the script very easily. So you can submit one thing and you get 1,000 copies running. Can you use a variable in PBS job name? I haven't tried that, but here's what I would do instead. There's actually two different ways to specify. So I can either put the $PBS -n in the script, or I can do this. I can specify in the command line. So I can do q sub -n. So let's do this PBS script. And so that submits a job. And notice in my PBS script, I had capital N in there, so you'd think my job name is going to be job name. But if I look, my job name is actually Brock P, because that's what the environment variable user equals. So if you specify the PBS option on the command line, it actually overrides what's in the file. So I would use, it definitely works if you put it on the command line rather than in the file. So you can definitely do what you're trying to do. Just put it on the command line instead. That makes sense? Yeah, so actually all of the PBS options you can put on the command line. None of them actually have to go in the file, and the command line always wins. And so that's actually going to be handy for something I'm going to show you next, which is what's called an interactive job. So these were all batch jobs. They go into the system. Oh, it looks like I had another question though. How can I stop the job in between? Do you mean stop an already running job? So qdel, that deletes a queue job, also works on running jobs. So if you run qdel job ID, we'll actually go out to the system where those jobs are running and kill them all off, and you'll get your .o and .e file, however they got crushed, and free up the processor. So you can use qdel on both queued and running jobs. Is that what you wanted? Okay. Go ahead and feel free to keep the questions coming. I'm just going to keep throwing out information. So I'm going to show you what's called an interactive job. So we've done these batch jobs thus far, these standalone, long-running, really meant for production type work. But what if you want a lot of processors to do something, some sort of testing? Well, what I can do is I can run q sub -I and then my PBS script. Now remember how the command line and the options inside the script kind of get combined together. So my script says give me 6 processors with 700 megs of memory. So you can put all those into PBS file, but if I use minus capital I, what happens instead of just submitting the job, see how it says queue sub waiting for job to start? Well, what this is we see it in the queue as a normal job. So here's my queue job waiting to run. So it still consumes 6 processors, everything like that. But when this starts, instead of running the commands that come after the PBS options, what it's going to do instead is it's going to log me into the compute nodes. And so this makes it so that I can type things by hand. So if I'm working on something, developing something, and I need, a lot of memory or a lot of processors, but it keeps failing in the first couple of minutes, don't keep submitting the job over and over and over and over every couple of minutes and then wait for it to run. Queue sub an interactive job, and when the job starts, then you can just sit there as though you're running this in front of your own computer. The difference is I'm going to have 6 processors guaranteed with 700 megs of memory for 1 hour. When I type exit, the job finishes and it just goes away. So the job should start here momentarily because there's plenty of free processors for this allocation. See, sometimes it takes a long time for jobs to start because we only start them every so often. But interactive jobs are super useful, especially if you want a lot of processors or a lot of memory. That said, if you do interactive jobs, don't leave them sitting around not doing anything, because you're going to tie up those processors so nobody in your group or your batch jobs can't actually run anything. So when you're finished with your interactive job, be sure to exit out. So see, now my interactive job has started. It says job is ready, and notice it put me on NICs 5542. So that's the compute node I was assigned. So if I run cat PBS node file, here's the 6 processors I was assigned. So if I did something like MPI run hostname, there's the 6 processors. So if I manually ran an MPI job now, it would automatically know the 6 processors. So this is the same as a batch job, but instead of having the script run everything, I get to run it by hand. So I could modify some code, recompile it, run it again right away, and not have to keep starting jobs and ending jobs over and over. So these are super useful, and you get that by adding on that minus capital I. So I can do a batch job completely, or an interactive job completely without a PBS file. I can just say pound PBS, minus I nodes equals, or prox equals, 12. All those minus L, minus M's, minus V's, all those, I just put them all in the command line here, and it'll start up for me. So that's an interactive job. So then I want to show one other thing. So for those of you who need to have CPU layouts different, or for performance reasons want to control how your CPUs are laid out. So right now we have this prox equals 6, which gives me 6 processors in any type of layout. Well, what if I wanted a single node with 6 processors? This would be for like a 6 processor shared memory job, like a threaded code, basic MATLAB if you're using its basic parallelism, not its distributed computing toolbox, but the basic parallelism that's built into all MATLABs. Or a threaded LU solver, something like that. So you need them all to be in one machine. So you can't have this 6 machines with 1 processors each. What you do is you say nodes equals 1 colon ppn equals the number of processors you want. So this means give me 1 node with 6 processors per node. And so that gives you 6. So it's still 6 total processors, but I'm saying make sure that I have 6 in 1 node. You can do this. So this now actually means 12 processors. So what this is going to give you, it's either going to give you 2 machines with 6 processors each, or 1 machine with 12. We'll always dense in, but basically we have this multiplier now of 6. On Flux, the highest you can go on normal Flux is 16. So we have machines that have 16 processors inside of them on normal Flux. So if you have a shared memory thing and you have a 16 processor allocation, you can request 16. But again, we have fewer 16 processor machines right now than we have 12 processor machines. We have 12s and 6s. But we're upgrading those always, so always pay attention if you're curious about getting larger shared memory counts. If you're on Flux M, large memory Flux, that goes up to 40. There's 32 processor and 40 processor nodes in large memory Flux. And in normal flux, there's 12 and 16. Note though that so if I go back and I say, nodes equals 2, ppn equals 6. So the total number of processors here I'm asking for is 12. I may get one 12 processor node. If you explicitly want to force 2 nodes with exactly 6 processors each, there's a different syntax, which I won't show here because it's rarely legitimately used. So I'm not going to show it. If you really think you need that, contact me at hpc-support, and I can show you how to do that. But again, it is rarely legitimately used. It should really only be used in certain benchmarking cases, and if you're doing that, you should have some other options that we're not showing here, like how to not share a machine with anyone else, make sure you run the same processor type, etc., so that between runs everything is the same. So this is how you can kind of say, like, give me larger chunks of processors and fewer nodes. So if I want 12 total processors, I could change this to 6 and this to 2. That keeps me from having more than 6 machines ever to communicate between. So you may find for your MPI codes, your parallel codes, that sometimes having fewer machines to communicate to is faster, and so you may want to force more processors per node. But the fewer you have per node, the faster we can find a place to run your jobs. Because right now it's easier for me to find 6 machines with up to 2 processors free or more than it is for me to find machines with 16 processors free or 12 processors free. Okay, so let's talk about these accounts a little bit more. So on Flux, you need an account or an allocation to actually run jobs. You can search online for that information, or you can send us an email at hpc-support@umich.edu for what those are. But how do you know which accounts you have access to? So there's a little command called mdiag, and you say mdiag -u, and you put in your username, and you get this list here, this A list. And so you'll see here that I have access to, in terms of Flux allocations, BROC-P Flux, CAC Staff Flux, Crash Flux. I have a large list here. It's rare for you to have this many. I just have this because I've had to help a lot of people. So this A list, this comma list, is any valid value you can put here. It has to end in _flux or flux m to, it has to end in flux basically to be submitted to Flux. So if the thing I'm supposed to submit against shows up here, I can submit against it. If you expect to work for a certain professor or a project and he says submit against this and you don't see it in this list, that means you haven't been added to it yet, and the responsible party for that allocation needs to contact us to add you. It's very quick, but still, don't find yourself not being able to run jobs because you didn't check ahead of time that you could submit against it. So then how can you check the information about that allocation, like how many processors it's allowed to use? So let's take Kevin's allocation here, and you can run mdiag -a on the account. And sometimes this takes a little while to run. But this is going to tell you things like max proc and max mem. So it'll tell you the total number of processors. So in this case, the maximum number of processors for Kevin's allocation is 660. So remember that showq command? Showq running account equals that one. So if I see here, his max proc is 660, but right now he's only using 108. So that's how those match up. So the -A in your PBS script corresponds to one of these accounts, allocations, that has a certain number of processors it's allowed to use. And then the showq -w account equals that shows you who's currently running against it. And so that's how those all mesh together. You can get the status of them. Max mem, let me explain what this is a little bit. So we actually track two things. We track processors and memory. So remember the pmem, 768 megs by default, and you can request more than that. Flux is built around 4 gigs per processor. So when you get an allocation, if you get a 1 processor allocation, your max mem is going to be 4,096 megabytes of memory, or 4 gigs of memory. So you can run a 1 processor job that requires up to 4 gigs of memory, but no more. The machines may have more than that installed, but if you try to request more than that, your allocation doesn't support it. If you have a 10 processor allocation, you'd get 40 gigs of memory you can allocate. Now the machines have more than 40 gigs of memory in them. So what you can do is you can submit 9 one processor jobs that all take the default, say they all take some small amount of memory, 1 gig, way less than 4. So I've got 10 processor allocations, so I can use 40 gigs of memory. I submit 9 of those processors asking only 1 gig. That actually means I have 1 processor left and 31 gigs of memory to allocate. So I could actually submit a 1 processor job that asks for 31 gigs of memory. That is valid. Because once you have your allocation of so many processors and with that comes so much memory, they work as 2 different buckets that you pull from. So a bunch of high processor, low memory jobs can coexist in the same allocation with low processor, high memory jobs. And so even though we say an allocation is 4 gigs per core, or on large memory 25 gigs per core, you can actually request more than that per core on a job. But if you run out of memory first in terms of running jobs, or out of processors first, the first one that you run out of is what's going to stop you from running. So you can mix those up. They work as 2 separate buckets. So hopefully it's a little confusing, but it's meant to be extremely flexible. And since we have 16 processor machines on Flux, that means we have machines that have 64 gigs of RAM on normal Flux. So if you have an allocation that has at least 16 processors, you can submit a 1 processor job that asks for 64 gigs of memory, and it will start and it will run. But it's going to use 16 processors worth of memory, but only 1 processor. But then if you have, say, some memory left, you can run a bunch of small memory jobs on your other available processors. It all gets spread around in the end. So that's kind of what I wanted to say about that, and that's how that works. So the way large memory Flux works is we have up to 1 terabyte in a node, and those have 25 gigs per core. So if all your jobs you're running need, I haven't done the math in a while, but it was something like 2 or 3 cores worth of memory, so like 8 or 12 gigs of memory per core. Large memory Flux works out to be cheaper for you because it's built with more memory per core. You're not paying for all the hardware without necessarily using the processors. So that's actually everything I had in terms of PBS and how to actually submit with it. You can send us questions if you have more at hpc-support@umich.edu. I just put that in the chat box. But you can also feel free to ask questions now or anything, any hypotheticals or things you're curious about. Go ahead and type them in now and I'll answer them. How to transfer files back and forth. Actually, I won't do that right now because I already did a webinar on that. If you look on the YouTube page, which I included before, there's a webinar on there, like a data management one. We cover it on there already. And also there's a whole listing of mini videos for how to use CyberDuck and stuff to FCP files back and forth. If you still have trouble after looking at that, send us an email. We can send you more information to make sure you actually see, but that's outside the scope of what we're trying to cover right now. I mean, we'll help you with it. It's just outside the scope of what we're covering with everyone else right now. So, any other questions? Any questions other than PBS ones, I can direct you to information like I just did there. Or if you have anything more involved, feel free to send them to hpc-support. Otherwise, we're all set. Again, this is being recorded, and so we will post it to the webinar archive, and so you can refer back to this later. Okay, well, thank you very much for attending.